we can consider a random walk instead of considering the exact paths between two nodes in a graph. An example of this is the personalized PageRank algorithm. Note that PageRank itself is one of the early algorithms that was used in the Google search engine when it began working. In this algorithm, you define the stochastic matrix P as follows. Now, to use this matrix P, you have this equation. You have QU equals CPQU plus 1 minus C EU. You can consider this C as some sort of a probability that kind of chooses one of these cases to be assigned to the QU. Now, EU is a one hot indicator for node U, and QU on index V is going to give us the stationary probability that a random walk that starts from node U visits node V. And you can see that this C here kind of determines certain probability for restarting at node U. And if you don't have this restarting mechanism, you're going to end up with some sort of a variant of the eigenvector centrality theorem. But now, when you're considering the importance of each node, you also have this restarting mechanism that can also add something to the system. Now, the solution to this recursive equation is going to be QU like this. And now, having solved Q, you can define the random walk similarity of node U and V like this. This is U, this is V, this is V, this is U. And what this here says is that the similarity between two nodes U and V is measured by basically how likely we are to reach one of these nodes by a random walk procedure that starts from the other. Next, we're going to talk about a pretty important thing in the graph theory called graph Laplacians and spectral models. Now, these concepts are mainly motivated by learning how to cluster the nodes within a graph and learning low-dimensional embeddings for the nodes of the graph. Now, we have talked about the adjacency matrix A, and they are pretty good in terms of representing a graph without any loss, even though there are some sorts of like redundant representation. There are, however, alternative matrices for representation of graph that have certain useful properties, and one of these matrix representations, which is the most basic version of the Laplacians. So Laplacians are basically formed by applying certain transformation on the adjacency matrix itself, but the most basic version of it is this. L equals D minus A, otherwise known as unnormalized Laplacian. Now, consider that we have a simple graph and we have this. D is the degree matrix, in which you basically have the sort of a diagonal matrix, and you have like the degree values, and A is the adjacency matrix. Now, let's go over the three main important properties of this Laplacian, and then we're going to go more in depth in terms of proving them and kind of investigating what other properties it has. So the first thing is that L is symmetric, meaning that the transpose of L is equal to L. And L is positive semi-definite. Two, or the second property, is that if you have X, so if you have this, you know that so based on the fact that L is D minus A, it is a member of this subspace. So what you have here is that if you assign a certain value to each one of the nodes, and if you perform this equation here, what you're going to end up having is going to be this. Meaning that for each edge, you can have this value. And the third one, which is kind of pretty similar to the first one, is that L has V non-negative eigenvalues, and that basically is kind of the same as being positive semi-definite. So you have this format here, and we're going to discuss why this part is equals, not larger than equals. One quick note here is that in discussing the different properties of the Laplacians in this part, I'm going to refer to basically use this notes from the An Algorithmist's Toolkit Lecture 2 by Jonathan Kellner. So let's go back to the definition of unnormalized Laplacian, which was L. So Laplacian of graph G is the degree matrix, or the degree diagonal matrix of degrees, minus the adjacency matrix for this graph. Now one question is, if you have a matrix or a vector X, which is a member of RV, and X for node U, such that essentially U is a member of graph's nodes, and the graph being like this, this value indicates a numeric attribute for node U, which is a member of the nodes of G. Now, if you apply L, or Laplacian of graph G, on this, meaning that if you multiply this value and then take the ith element, what you're going to have is kind of interesting. So let's see. This basically means that you need to multiply the ith row of LG with X. So if you consider the ith row, the ith element would be the degree of node I. So let's consider this U. So the degree of node U would be the element that resides in the uth element, and then the other ones, you basically have any outgoing edges represented by -1. So these are basically the neighbors of node U. And then X here is going to have the numerical attributes for all of the nodes up until node U and everything afterwards. So if you multiply this two, what you're going to get is you have the degree of node U multiplied by the attribute for node U and minus for basically all of V's that are in the neighborhood of U. What you're going to get is that you have the values of xv. Now if you factor out the degree of node U, you have the degree of node U multiplied by the value for node U minus the average value for a neighbor of U, because this is now divided by the degree of U. So here is the average of this attribute over the neighbors of U. Now let's talk about some of the important properties. The property 1 that we want to talk about is edge union. What this here says is that if you have two graphs, such as G and edge, such that they are defined in the same vertex set, but they have different and disjoint edge sets, meaning that the intersection of E1 and E2 is empty. Then if you consider the graph which is found from the union of these two, it's going to be LG plus LH, and this is the additivity property for the Laplacians. And it is pretty intuitive. The second one has to do with the isolated vertices, meaning that if you have a vertex u, so if you consider the graph G composed of set of nodes and set of edges, and if you have a node u such that basically there isn't an edge E in the set of edges such that node u is a member of it, then you can conclude that the corresponding row and column in the Laplacian for this is going to be 0, meaning that if you consider the Laplacian LG, and if you have I, this is going to be 0 for all j, and also a column as well. So for all j, row and column associated with u are going to be 0. So if this is the Laplacian and this is the youth index, this plus sign here, it's entirely going to be 0. Now let's talk about disjoint union. If you have the disjoint union of G and edge graphs, the Laplacian of these two is going to be defined like this. So it's going to be the direct sum of LG and LH. Now let's see why this is the case. Now one thing to note is that the disjoint union of G and edge is going to be this. And when you have this graph in mind, this means you use all of the vertices with graph G's edges. And of course, when you have this here, you mean that you again use all of the vertices, but this time with graph edges. So based on the previous properties, we know that L, this is going to be LG 0, 0, 0. And you know that for this one, this is going to be 0, 0, 0 LH. And these two have the same dimensions. Now, based on this definition right here, and based on what we discussed, given the fact that now we have this graph, and these are defined on the same vertices, but with no intersection with the set of edges that they have, we can use the additivity property, and then we have summation of this and this, which is LG, LH, 0, 0. One very interesting thing that this implies is that the Laplacian is the direct sum of the Laplacians of the connected components. Now in the previous example, if LG has eigenvectors v1 to vn with eigenvalues lambda 1 to lambda n, and then if LH has eigenvectors omega 1 to omega n with mu1 to mu n as the eigenvalues, then the disjoint union, the Laplacian of the disjoint union of G and H is going to have eigenvectors of this. It's an all 0. All 0 again. Like this. And the reason why is that you have this right here. So if you multiply this by, for example, this eigenvector for the new Laplacian of the disjoint union, what you're going to get is this is going to be LG mu1, and this is going to be 0, and then it's going to be lambda 1 v1 0. So the overall eigenvalue would be lambda 1 with this eigenvector. Now here's another important property. Consider that you have a graph G that has this set of vertices and set of edges. Sorry for the bad handwriting, let me correct this. Now let's say the cardinality of the number of nodes is n and the number of edges is 1, meaning that without the loss of generality, you could assume that epsilon is going to be an edge E, which is V1 and V2 in this system. Now, if you consider this unnormalized Laplacian, LE, or the Laplacian of this graph with only one edge, is going to be 1 minus 1 minus 1, 1. Everything else in the graph is going to be 0. Now, if you consider the entire graph as kind of like a union of one-edge graphs on the same set of vertices, you can basically use the first property that we mentioned, the additivity of Laplacians, and then the Laplacian of the graph G for each one of the edges would be the added value of each one of these Laplacians. Now, here are some important properties that kind of stems from this. If you consider this matrix 1 minus 1 minus 1, 1, this is basically 1 minus 1 and 1 minus 1. So it's going to be 2. So what this implies is that if you multiply this by this value here, you can see that this part kind of ends up being a 1. So this right here is the eigenvalue with the eigenvector of, the eigenvector with the eigenvalue of 2. So that's one thing. And this decomposition, what it implies is that if you have x being a vector of x1 and x2 with 2 attributes for node 1 and node v2, what you're going to have in doing xtle x is going to be x1, x2, 1 minus 1, 1 minus 1, and then you're going to have x1, x2. So you can think of this as some sort of a differentiation, and then you're going to have x1 minus x2 to the power of 2. So in terms of quadratic form, you can consider the entire graph like this. You can substitute LG with this new version, and then for each edge you can have x t l e x, which results in the fact that for every I and j in the set of edges, you're going to get xi minus xj to the power of 2. Let's see an example of this. So you have node 1, you have node 2. The L is going to be 1, 1, minus 1, minus 1. And let's say you assign the value 5 to this, and let's say x1 to this and x2 to this. Now you can have basically xtlx computed like this. You can have x1, x2, 1 minus 1, 1 minus 1, and x1, x2. You do this multiplication, you're going to get x1 minus x2 minus x1 minus x2 times x1 and x2, which is going to be x1 times x1 minus x2 minus x2 x1 minus x2, which is going to be x1 minus x2 x1 minus x2, which is going to be this. So one thing you can conclude here, and it's kind of important, is that adjacency matrix for this matrix, for this simple graph, was 0, 1, 1, 0. So you have this for every edge in the graph, not for every one in the adjacency matrix. Also note that here, this was a custom customly selected x. So for any x, this is going to hold. And this is another indication that the Laplacian LG is positive semi-definite. Let's do a review over the concept of positive semi-definiteness. If you have a Hermitian matrix, or in this case a symmetric matrix, M is positive semi-definite, or M is positive definite, if for any random or arbitrary vector that you choose, this value satisfies these two inequalities, meaning that if for any x that you choose from the space of basically these vectors, this value is larger than or equal to 0 or non-negative, then you have positive semi-definite. If everything is positive, meaning that it is not 0 or higher, larger than 0, then it is this. Now, an important corollary of this is that if you have a matrix that is positive definite or positive semi-definite, let's consider the positive semi-definite first, and the positive definite is pretty much the same. For every x, you have this equation being valid. Now, if you consider any eigenvector for matrix M, let's consider that V is an eigenvector of matrix M. In this case, a right eigenvector. What you have is essentially this. So you can substitute x with V in this equation and get this, which in turn becomes this. And we know that this is going to be larger than or equal to 0, or larger than 0 in case of the positive definite. And according to this, you can conclude that lambda is going to be non-negative, because this is always positive. And this basically means that if you have a matrix M, which is a symmetrical Hermitian matrix, and it is positive definite or positive semi-definite, this constraint applies to all its eigenvectors. Sorry, its eigenvalues as well. Now you can consider the matrix M in its eigenbasis. Therefore, you will have M defined as QT, lambda, and Q, where this is the diagonal matrix of lambdas. And then you, for example, know that this is going to be essentially this, and this is going to be larger than or equal to 0. So we know that, okay, if you consider this is going to be larger than or equal to 0 for all possible y's, only if lambda i's have the same properties, meaning that they are larger than or equal to 0 for all of the i's. And the same thing applies for the positive definite, except that you use a strict version of this inequality. Now, another lemma is that if you have a positive semi-definite matrix, for example, M, there exists a matrix A. Let's say this is a member of M. There exists a matrix A such that M can be factorized this way, or decomposed this way. To prove this, and by the way, this is an if and only if relationship. Let me actually write this a little bit better. So M the symmetric matrix M, a member of RMM, is positive semi-definite if and only if there exists a matrix A such that M can be decomposed into A transpose multiplied by A. Now to prove that, first let's prove this side. So again, if you consider the eigenbasis, you had this. And since this is diagonal and non-negative, you're going to get this. And obviously this is the same as its transpose. So you can formulate M and decompose it this way. And this is going to be essentially the diagonal matrix like this. And that would be it. So this is the proof for this side of the equation. Now for this side of the equation, you assume the otherwise. You assume that M is ATA. Obviously, for any x, if you consider this, it becomes this value, which is larger than or equal to 0, and this completes the proof. Now let's come back to the definition of the Laplacian and talk about factoring the Laplacian. Okay, so we know from the previous discussion that if we have L, and L is positive semi-definite, there is the eigenbasis, and you have this sort of format for it as a factorization and decomposition of it. But the question is, can we have like a better factorization as well in terms of the intuition and what it means? And the answer is yes. Consider the graph G, set of nodes, set of vertices. Consider you have n vertices and m edges as usual. Let's define something called the incidence matrix, or this. This incidence matrix is going to be a m by n matrix in which each row is associated with an edge and each vertex is associated with a column. And let's see what exactly each one of these values are. If you consider one value here, the value of the incidence matrix at elements E and V corresponding to edge E and node V is going to be defined like this. If E is like this, and V is smaller than omega, this value is going to be positive, it's going to be 1. Now if E is a V omega such that V is larger than omega, it's going to have -1 and 0 otherwise. The thing we want to show is that LG can be factorized by the incidence matrix. And obviously if you show that, it's also another proof why LG is positive semi-definite, because it is in this format. And this format is also symmetric. To see this, note that if you compute this and the ijth element, you're going to have basically this. Which essentially squares this value. So for every E incident to VI, you're going to have a value of 1, and what exactly this gives you is the degree for node VI. Note that this is for the case of I being equal to J. In the other cases, let's say I is not equal to J. Let's say there is no edge between I and J, or VI and VJ. Therefore, in this part you're going to get this. And since there is not a case in which both of these are non-zero, this is going to be 0. But when there are, edges like that, what's going to happen is essentially this. You're going to have this. So again, for the edges, you have this format. And we know that, in these edges that are incident to them, what happens is that one of them is going to be positive, the other one is going to be negative, because either Vi is smaller than Vj, or I is smaller than j, depending how you exactly treat the indexing of the nodes, or the other way around. These two cannot be positive at the same time, so this is going to be negative, which is kind of equivalent to that d minus a definition that we had for LG. We had the degree here, we had this -1 and 0 is there, so we have this thing as a proof. Therefore, when we have a matrix, when we have this equation here, we have this. And what happens is that for every edge in E, you have xi minus xj to the power of 2. Again, to see why, consider this incidence matrix. You have an edge E, which, is that formula. Sorry, for hij in E. So, if you notice, a square comes from the fact that we had this, so this would become this. Now here, we have ith and we have jth, and obviously one of these, and in this case, we are assuming that I is smaller than j. This is going to +1, this is going to be -1, but it doesn't really matter. Multiplication of this with some attributes per node is going to lead to xi minus xj. And since this is this, we're going to have xi minus xj to the power of 2. Another important thing to discuss is about G being connected and the null space of LG. So let's see what we're talking about here. Let's say X is a member of the null space of L. This means that LG times X is going to be 0. This means that xt LGX is going to be 0. This means that this is going to be 0. Now what that means is that for every I and j that form an edge in this graph, the attribute value for I and jth nodes are exactly the same. So what this tells you is that the null spaces, so like the values of the null spaces, are a coefficient multiplied by 1, meaning that the same value being assigned to every node. So this basically means lambda 1 is 0. Now, one thing to mention is that what we discussed earlier about applying the Laplacian to a node, we remember that this was something like this, but this was the average attribute for the neighbors of xi. And that way, basically, it's also obvious from this that if all the values for all the nodes are the same, this is also going to be 0. Now, one corollary is that if G is connected, lambda 2 is not going to be 0. And essentially, the dimension of the null space of LG is exactly the number of the connected components of the graph G. You could use induction to get to this, that the dimension of the null space of the LG is the exact number of the connected components of G. But some simple examples about this is something like this. You have, for all of the edges, you have this equation, LGX and when you have like something in the null space of LG, this becomes 0, this entire thing becomes 0. So when the graph is connected, you know that it's basically multiples of 1 that makes this 0, and that kind of removes one rank from the rank of your LG matrix. And let's say you severe one connection, so you have something like this. Now because there is no edge connecting this node to these two are bound to be the same. This is not, therefore you have one dimension more in your null space, and that you can basically use this and some other things and with the induction prove that the dimension of the null space of LG is exactly the number of the connected components of G. One last thing to mention is two different variants of normalized versions of the Laplacian. So using the degree matrix, you could have this for symmetric normalized Laplacian and this for the random walk Laplacian. And similar properties hold. There are minor differences. For example, the eigenvectors could be scaled by certain powers of d, but everything else mostly hold. One of the things that we discussed prior to basically going to graph cuts and clustering, one type of clustering that we had discussed so far was based on the definition of the Laplacian, like the unnormalized one, for instance, which was defined as d minus a. And we realized that because of the definition of the Laplacian, if you have a graph, for example, something like this, there are a couple of ways to think about it, but one easy way to think about it is this. Let's say you want to consider the null space of L, and based on what we discussed in terms of the definition of L, we knew that if this being a scalar, the null space of L, this would be basically a basis vector for it, and the dimension would be 1. And then we discussed that if we, for example, severe disconnection, meaning that, let's say we remove this one, now the option that you have is that you can add a uniform, basically assign a fixed number to this and assign a fixed number to this, and we realized that the number of 0 eigenvalues of L, or in other words, the dimension of the null space of L was equal to the number of connected components. And this was one way of basically clustering the nodes based on the connected component that they belong to. Now this time, let's assume that our graph is fully connected. Now the question is, can we use the same thing that we used, meaning Laplacians, in order to basically perform some sort of a node clustering within a fully connected graph? And the answer is yes. So now we want to talk about graph cuts. Note that we want to talk about what exactly is the motivation and operation behind this notion. Laplacian spectral clustering. And to know that, the first thing we need to do is to kind of talk about something called an optimal cluster. So first, we're going to define something called a cut in the graph. So let's say your graph is this set of nodes and this set of edges, and let's say V can be partitioned into A1 till AK, such that these are basically, it's a partition, so AI intersection with AJ when I is not equal to J is empty. So based on this partition, which basically gives you K non-overlapping subsets, because it's a partition again. So you have K non-overlapping subsets here. How you define a cut is like this. You say that the cut is defined this way. Here is an example. In this case, you have A1 here, and you have A2 here, and your V is A1 union with A2. Now here you have nodes 1, 2, 3, obviously 4, 5, 6, and in this case, for each one of the k's, meaning for k equal 1 to 2, you're considering, so basically, let's do it for individually for each one of them. So first, let's consider the K1. What are the edges that belong to the set of edges that are in A1, starting in A1 and ending in the other one? So you can see that you have this, you have this, you have this. So basically you would have 3 here. You do that symmetrically for A2, you would have 3 there. So you have 3 as the cuts of A1, A2.